So let's go ahead and look at these equations. So we have xf, we have our displacement in the x direction, our displacement in the y direction. Everything that we're dealing with when it comes to projectile motion will come from these two kinematic equations. So let's say that we have something that's going to launch a ball, okay, in a given direction. Okay, and this vector here is going to represent the initial velocity. So we'll have, remember when we represent our vectors, part of it can go in this direction. So this is going to be our initial velocity in the x direction. And then you'll see another vector come up here. And this will be our initial velocity in the y direction. We have an angle that we can measure called theta. And we can use our sine and cosine functions. Remember, sine of the angle under consideration, this is theta, is equal to the opposite side over the hypotenuse. You guys remember that? Opposite over the hypotenuse. What is your opposite side? The opposite side is the initial velocity in the y direction. What is the hypotenuse? The hypotenuse is just your initial velocity. Okay? So you have the sine of your function in terms of velocity in the y direction and just the initial velocity. So this equation implies that the initial velocity in the y direction is just equal to the initial velocity times sine of the angle theta. And now let's do the same thing with cosine. Cosine of the angle is just equal to the adjacent side to the angle over the hypotenuse. And what we know is the adjacent side is our initial velocity in the x direction over the initial velocity. This equation implies that the initial velocity in the x direction is just equal to the initial velocity times not sine, but cosine of theta. Okay, so these two equations are going to be equations that we use in our kinematic equations to have more power, more description. So if we write our kinematic equations down again, and you'll see them right here, we're just going to write them down again, but we're going to replace our initial velocity in the x direction and our initial velocity in the y direction with these trigonometric relationships. So let's do that. So x will be first, x final, minus x final minus x initial equals to the initial velocity in the x direction times time plus 1/2 a sub x times t squared. And then we're just going to make our substitution now. So you have xf minus x initial, which is our displacement, those together. And we're going to have our initial velocity times cosine of the angle that we launch something with. And that'll basically take care of our vector, the direction of our vector, times t. So if we know the angle, then we'll know the direction because we'll define the angle. The angle starts on the x-axis here, and it starts off at 0 degrees. And then we move up like so, and eventually get to this point. This is 90 degrees, and then 180, okay? And then 270, and back to 360. So we have V naught cosine of theta times t plus 1/2 a sub x times t squared. Okay, this is a nice equation. That's our most general form. It is the one that we'll be using when coming to doing calculations for kinematic equations. Now, the next formula is just the y direction, which is yf minus y initial equals to our initial velocity in the y direction times t plus 1/2 a sub y times t squared. We make our substitution, and we will get the following. Our initial velocity times sine of the angle theta times t plus 1/2 a sub y t squared. And that's it. We'll use both of these equations, and let's see which number we'll give them. Okay, let's give this one 8. Let's give this equation, let's call this 8. Let's call this 9. And let's call this 10. And let's call this 11. So we'll use equation 10 and 11 for our kinematic equations. This is the theory. We have to apply it. We're going to have to apply it.